This is a new joke to me. So let me do something. This is presumably meant to be. Let me talk to you while I'm waving this. So the thing is that this is has a very deep philosophical point, this topic, and what I'm going to tell you is that the only way that you can avoid me talking about this is if you end up in a hospital or accompanying some person that ended up there, unfortunately, and if you don't want to know about what this is all about, then I think you are just about right. So I wanted to talk, does this really work? About this topic because of the fact that I think that we have now come to an understanding of what we understand and what we do not understand. So I'm from this place which is in Finland. Lasse, with whom we've been doing all this stuff, is somewhere around here. Do I see him? Yes. Are you awake, Lasse? Yes. And Henri Salmejoki has been already presenting some of the things that I want to show you in his poster, which is about the last part of this talk. And there have been a number of people that have been crucial to the things. Peter is somewhere here, I suppose as well. Are you? I don't see you. Hand up, hand up, hand up. In the last row, of course. And so on, some PhD students. So why do I want to talk about this? I want to talk because I think it's interesting in the sense that this, apart from the fact that the topic is interesting, it is also interesting the way our thoughts develop about the subject. And the dislocation avalanche means, of course, deformation avalanche is a thing that we have heard about 100,000 times so far, at least so I calculate myself. And the thing is that what did we actually learn about this is one question. The story, of course, develops with years. And the second thing is that what do we actually understand now? What have we actually learned? Okie dokie. So there's this old phase diagram idea of coming from granular systems, more or less, that hey, wait a second, there could be a non-equilibrium phase transition, and then people started to think about this matter also in context of plasticity, thanks mainly due to these micropillar experiments that we heard already about. So you get stress strain curves that have bumps, and of course you get other things, acoustic emission and whatnot, but the fact that the plastic deformation is intermittent on small scales becomes evident if you start doing that. And then you end up with these questions that related to physics, that if this is a real phase transition, so what's the yield stress, how does it actually rise, what is the theory of this thing, and then there are questions that are obvious that it's not maybe so evident in the case of plasticity that what is the phase time like, what are the quantities does it look like, what is the order parameter, what are the control parameters, and having done that, then you start to wonder about what is this transition like. Is it second order? Is there a correlation length? And what is the spatial interpretation of this correlation length? That presumably is hidden in this kind of jerky stress strain curves that you mentioned. And what you are left with, or you were left with maybe 15 years ago, were the distribution of bursts, the avalanche sizes that you get from this kind of stress strain curve, so jumps in stress or strain. And then that's what we wanted to understand. So go a step ahead. There was this paper in Science in 2007 where people did actually complicated simulations. So this is what the real dislocation systems looks like. You have a bunch of topological objects that are line-like, and what you do is that you put them in the computer and simulate, and then you take data and you take a number of systems that are fairly small, micrometer level. Now that we have been much more elaborate and intelligent and have bigger computers, we can maybe go to 2 micrometers inside. And what you do is that you measure the avalanche distribution. It looks like this. It has a cutoff that you can say it comes from the fact that you have a natural scale to the avalanche. It comes from where you load. There's a machine equation and a stiffness and whatnot. And then you conclude that, hey, wait a second, it has to be so that this is actually a deepening transition because you match so very well what you see in statistics from what you would expect in 3 dimensions when you're close to a mean field limit of deepening. Very well, or maybe not so. So, but then people did something which they evidently do very often, and they kept working on this topic. And here's an example of Nacta material. Authors can remember this is, of course, shows you just simply that you can measure, as for instance Peter was saying, you can measure this avalanche size distribution very many ways, and the results that you get start to differ. And meanwhile, the zoo of exponents that have been quoted about what you actually find from this experiment, this is too hot actually, then this starts to get a little bit complicated because you have realized this is not 1.5, it might be something else. And all these things that you could imagine, you can look at single crystals, they are nice to do, and then you say that I'm working on very technologically important thing, I could do polycrystals, I could do FCC, BCC, SCP, and you get various results. So the question is that where did this deepening then go, because all kinds of results are not maybe in agreement. And then you had this original idea that said that, well, this is basically just due to the fact that you have dislocations that are in a random force landscape, and you push them enough, then there's a critical stress, the yield stress, then they move around, you have continuous plastic flow. And in the proximity of this point, you have avalanches. And this is what I say here. The only complexity that you would think about this if you start argue like this is that there are two things that are important. One of which is that these very long range interactions, elastic interaction of dislocations, cause this kernel is also anisotropic and not positive definite, but that's another story. And then the thing is that then the idea is such that you sort of expect that this landscape is like in a good deepening quenched, but of course it slowly changes as the dislocations move, so well. Anyway, so what we do then is to resolve this thing is that we take a toy model, and I like to tell this to metallurgy people that we are, as a physicist, what you do is you take a simplest case of edge dislocation that you move around, and you say that it's an equation of motion, and what you have in this thing is that of course you have interactions that are usual kind of complicated character, and the thing is that this is a more or less zero temperature. Theoretically speaking, at least if you want to coarse grain a molecular dynamics simulation, what you do is that you figure out what the mobility is for the dislocation, plug it in, you forget about temperature, and of course you can play with these things. But that's how you can test these things if you just want to say that let's do this in the reduced dimensionality. So, because people thought, I've been talking ad infinitum about the case of amorphous plasticity and what you learn about if you do large amplitude oscillators. I cannot yet avoid pointing out this paper that did a long time ago actually where we did the same things. You have Lissajous plots, and what you figure out from this amplitude of the hysteresis loop and how that scales as a function of stress that you apply and the frequency of the external stress that you do, and you get all kinds of interesting results. And the thing is that why I'm pointing out is just because of fun, and secondly this leads us to the question that, well, is this really deepening? What is the yielding transition like? I mean, if you look at these things, the central question is such that you have a bunch of external maximum stress values, sinusoidal loop, blah, blah. And the question is that, well, can you tell me what is the particular value here for the yield stress of this system? Is it a relevant question? Okay. The real story starts from this paper that we did 5 or 6 years ago, where the question was simply so that some of us, I don't remember this collaboration, it's like a high energy physics, there are 55,000 authors in papers. So the question was that what happens if we actually mimic an experiment? So let's just do a shearing experiment on one of these two-dimensional systems and see what you would actually get and how that actually compares to what the real deepening transition. Here's a long-range deepening. If you do that, you increase the force, you get avalanches. You see that they increase in size very slowly, and in the proximity of a critical point, you start to see the divergence at values of external stress that depend on the system size to apply, so you get the corrections to phase transition critical value. And to make a story short, now if you do these models of two-dimensional dislocation systems, what you see that the avalanche sizes actually do not follow that kind of behavior at all. You get an exponential increase as a function of a number of particles in the system and such that there's an amplitude here, and that does not really look like that at all. So something else happens, and what else happens? Well, of course you still get scale free behavior, but you get the scale free behavior at any stress applied, so it's completely different from a typical critical point. So here are distributions of avalanche sizes in different cases. The simple point is that you get a powered behavior and a cutoff, and then you can summarize this how this cutoff actually behaves as a function of the stress that you apply. Larger are the stresses, so you follow stress strain curve, you pin it, you look at the avalanches inside the pin, and the pin has a cutoff that increases with the stress that you apply. This thing was tested in various contexts, like, for instance, what's the precise model and how many dislocations you put in the system. And the thing here, why this is important, this tells you that you can make a coarse graining step. You can either say that you follow directly the dynamics of dislocation, whether it goes slowly or fast during avalanche, then you can do a cellular automaton, say that even it moves or doesn't, the velocity is the same. Still you get the same kind of integrated avalanche size distributions. And last but not least, here you have examples of what happens if you scale all the data such that you put in a thing that takes into account how the cutoff scales with an external stress. There's an exponential thing here, and there's a number of sublinear scaling, and there's a number of dislocations put in the system. This is completely weird and doesn't particularly agree with any kind of critical point behavior that would expect. This is what I'm saying here. You recover criticality. You can say that there's, well, at least you can fit the data such a way that these avalanches have a Paulo-like behavior with a cutoff, and this cutoff scales in such a way that it looks a little bit strange. But you should remember which way it looks strange. And if you look at things like, that for instance, what's the typical avalanche size in this system as a function of number of dislocations, you see that if you compute that one, that it is something that gives you a value which is reasonable, it doesn't diverge faster than the system size would actually do. So we did that, and then there's another intermezzo that we had this thing that just to show that, well, if you really want to grit your teeth, do like this, don't do that while you're sleeping, then what you do is that you discover that you have pinning again. Of course, to get deep in here, what you need to do is that you have to have at a competing mechanism. Well, this was the equation most that was showing. Let's plug in here local pinning centers with some properties. Doesn't really matter as long as they are local. I mean, the interaction local in range. Here's an example of such a system. As you would simulate it, here these points are the solute atoms. This is 2D, but you can, as you will discover, do this in 3 dimensions. You get the phase diagram really saying that, well, if I'm at low enough stresses, how this thing that where disorder is not relevant at intermediate values, you get a real phase transition, and then if you add enough of that, you kill it all. And I think some people have done this experimentally. This is maybe something we should discuss at some point, actually, how to reconcile these two views. But since we only ski together, maybe we should do this one. Just to show what this stuff actually looks like, here are these avalanche size distributions, what to get out of this thing, and you can, at the end of the day, you can collapse this all as a function of external stress, such that you can also look at how the cutoff scales as a function of distance to the external, to a critical yield stress. So this model, if you put enough disorder, what happens is that the disorder, so to speak, combines with the dislocation self-interaction in such a way that you have a real yielding point, not what I was talking about previously. You can get, well, that's avalanche durations, but the thing, you can get unrade creep such a way that you see that really you have a crossover to continuous flow. If you are large enough stresses, there's a critical point, and if you're far away from critical point, the Paolo decay of the order parameter goes away. And one thing which is important here is that if you look at how this guy, the yield stress actually scales as a function of the solutes, you realize that there's a funny scaling that tells that if you apply this to real materials, you are seeing fun effects in the same way that how you actually can increase the yield strength by increasing the strength of pinning or number of pinning defects. So here are three points that I wanted to make. First of all, well, there's no depinning, you have this kind of extended criticality, and some of these other points. And the question is now that if there is actually yield transition in such a way that you would like to, you have a point which is characterized by Paolo scale-free distributed avalanches, you can create that, but how does this point actually look like? How can I control it if I change the material properties in the model and the reality? What are how much can I actually tune that? So, because we are boring people and have big computers next door, the National Supercomputing Center is next to our campus, so the only thing that you can then do is that you can repeat this for realistic materials. And realistic materials means now that you do a 3-dimensional discrete dislocation simulation, this kind of soup. This is supposed to be a real aluminium on very small scales, and what you do again is that you compute average stress strain curves as a function of number of dislocation systems, and you can see that these are jumpy as always, and what you do at the end of the day is that you figure out that this looks pretty much exactly as what the 2-dimensional toy model does, apart from the fact that because this model actually has you have dislocation nucleation and such, you get more forest pinning because of the fact that the dislocation density starts to increase if you follow the stress strain curve. one of these reasons why these systems are so complicated is if this is again that you can show that it's not mean field like it doesn't really matter. These subplots are maybe something that show you how complicated this issue, because you can look at single dislocations as they behave, segments as they behave in this kind of three-dimensional systems. This is an example of a signal of a single avalanche. It has a peak and decays slowly, but then you have also collective avalanches if you go to larger avalanches. So there's a mixture here of a single particle behavior. Single particle means a single dislocation exploring a random force landscape. And then if you start to involve more and more dislocation, then this starts to look like what you would expect. Maybe not a really parabola for this avalanche, but something like that. The last of these plots shows the same thing again, in the sense that at small ranges you see that it's a 3D system, you get something strange because then you only single segments that actually participate in the avalanche. In larger scales the exponent goes down and you have a participation number is large, and as considers the typical avalanche size as a function of external stress that you apply a number of dislocations that your system has the same kind of feature as in the 2D case. One point here is the dynamics of avalanches, so this is that thing. And the second point is quite simply so that there's no deepening here either. And this is supposed to be a realistic crystal. So we probe this a little bit further as an analogy to what we know with amorphous plasticity, so that excitation spectra, meaning that what's the proximity of each point in a system, give it to make it a particle, or if you think about in terms of discrete systems, lattice models or whatever you want to call them, to the how close is each point in a system to actually getting unpinned. Well, you can do this thing also in these systems. You can take a 2D or 3D system, you can apply an increasing local stress to one of these topological excitations, be it a segment in a 3D system or one of these particles, and you can see that at which point, at which stress does this actually incite an avalanche, so then you get the excitation spectra. An important point here is again that what you see that these are scale-free, except if you have actually disorder, then you get a cutoff, and in 3-dimensional data is really shitty, but forgive me my language, but it still looks pretty much as you would expect, that there are extremely soft modes in the system that you can excite. So then almost done. I'll just give you a little bit of publicity for the poster of Henry out there. So we're looking at this thinking about this matter from another perspective, and the simple perspective that was the starting point of this story is actually quite too simple to be true, and that is to say that if you are thinking about the yield transition as a classical phase transition, then you would expect that the avalanches, if you approach that within its proximity, are more or less unpredictable. So the question was now that let's do this thing again that we did already, which said that follow a stress strain curve and the avalanches on that. Do these make actually the whole system unpredictable, or is there some degree of predictability left that the avalanches do not destroy? My guess was to begin with that this is actually such that discovered this complete nonsense that we cannot do anything, but well, thing is that this turned out to be exactly opposite. And so the thing is such that, well, this is not really a story of artificial intelligence, but it's a way of finding things that correlate with each particular sample's behavior in such a way that they tell you what it's going to be doing. So this is essentially exercise in fitting correlations. So that's what you fit correlation. You could replace this instead of this. I believe that this is supposed to depict a neural network, but in the absence of neural network, I would have a much better suggestion, which said that this could be a photo of Henry Salmejoki here, and then you're up with this thing. And the point here is such that we take the features of a dislocation system, so this is a bunch of topological defects at zero external stress, relaxed, and then we can do this exercise in two ways. We can look at it well, as you would do classes, you would quench in different ways. We did these quenchings in a million ways, and after you do that, you summarize this somehow with parameters that allow you to follow the typical stress strain of a sample. So here's what is a true lag. It has these avalanches, but the average behavior you get from these typical features of the original state actually allow you to guess pretty much that this is I can follow the black one because I didn't know what it looked like in the beginning of this system. I can follow the red one as I know what this actually looked like at the beginning without actually applying any external stresses. So why is this so? Of course, it means that the systems have a memory. And the main point of this memory thing is that apart from some uncertainties that apply because of the fact it's difficult to guess that when the avalanche activity actually starts, then makes you a little bit go down. The thing is that there are large-scale features in this memory such that they can become even more noticeable if you go to larger and larger system sizes. Larger, it's more predictable, it's kind of funny, but on the other hand, this is not a big surprise because the question has always been that why is this avalanche activity in plasticity so difficult to actually see in real materials? And there are various arguments about that, but the thing is that at the end of it, it boils down to the one way to put it, that the fractal dimension of this avalanche is always smaller than the space dimension of a system that you look like. So relative weight goes smaller and smaller if you get a larger and larger scales. Then you can look at that thing, like it's boring, and you can look at the relevance of features. So the idea here is quite simply that if you don't want to do status, but you want to understand what is important here, and what is the importance of the protocol by which you actually develop or prepare your samples, like we have heard about the case amorphous materials. So now you can look at as a function system size as to what features become more and more important if you go to larger and larger system sizes. And what you figure out from that is that more or less it is the geometrically necessary dislocation. So there's a memory of the system about what was the dislocation arrangement and the way they would like to organize themselves if you apply external stresses. And this feature, how important it is or it's not, depends on what the initial state looks like. So the imprint of a preparation protocol sits right in there. So that I've already told you. The question is now that we have done this all as an exercise to show that something is true. What we discovered was something more interesting, and we also discovered that what we originally guessed about how this would actually go is actually wrong, which said to discover the strong predictability, blah 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 blah. So what can we say about actually real crystals? Well, the thing is that I think that we have here well, it's not the kind of problem where in a hospital and you are waiting for your leg to be x-rayed, but it's a more pleasant problem that you cannot solve actually, and that is to say that we do not know how much data we actually need to make this work. So if I take two different small crystals, 2 micrometers linear size, compare them to each other, I do an X-ray diffraction measurement, I get some numbers. Can I actually tell from these numbers how different these are if I actually start to strain or compress or whatever they look like? Probably not much. So I have to add some other features. What are these features and how much of statistics I actually need out of this, I do not know. But in a sense of an exercise that can be brought into a conclusion, I think this is entirely doable. Summary. I think that we have now come to a point when we have a good operative understanding of what these systems actually look like. I've omitted some queasy details, but the question that whether the system actually exhibit deep in transition, and that is what actually explain where they look like they would have critical behavior, that it has been resolved. Of course, there are some other things. I just copied this thing that because it should look nice. This is some kind of thing where you want to do plastic deformation, some kind of whatever this looks like. Just a FEM model. And if you do a FEM model, you want to put in the good enough material model so that you actually recover the effect of what turns out to be all of this complexity that we are talking about here. And I don't think that actually exists. There are issues there that are clear if you look at the engineering plasticity literature. One of these things that we don't actually understand theoretically well, but that's what we see the signature of, what is this force landscape, that how it actually changes, like these mechanical noise arguments for amorphous plasticity. I'm looking at this thing on a single particle level or a single site in some kind of model, and the question is that how does this actually get influenced by its neighborhood? This has not yet been done, and maybe it would be worthwhile. But of course the question is such that this is supposed to be important experimental. I can do colloidal crystals which can be 2-dimensional just fine, but at the end of the day this is what basic metallurgy, what we are looking at. One thing that I think that if you want to sell this to somebody, is that you have to say that, well, we can do this actually make this actually useful for real materials when this wild or mild plasticity. One question, what is the yield stress? Can I tell that when this particular material has yielded 0.2%, 1.1%, that would be a mechanical answer to a materials science question. And the question is now that I want to a little bit wave a dog over tailor dog is this material designer aspect, and that is to say that if you can, with this kind of, I would not call them machine learning, but correlation arguments, catch some essential features of plasticity, maybe that is actually more useful than looking at power law exponents. This is a quote from Wittgenstein that I translated myself to English, and well, that much I can say. Sorry, Kirsten, for my bad German. And to finish, here are some papers. Thank you.